First, if class-agnostic NMS is enabled, we set C to 0, meaning all predictions are treated the same regardless of class. Otherwise, we multiply the class indices by max WH, a large constant, ensuring that NMS processes each class separately. Why is this class offset important? Since agnostic is false, which is the case here, we want to make sure that NMS only compares and suppresses overlapping boxes within the same class. By offsetting each class's bounding boxes by this large value, we push predictions from different classes far apart in space. This prevents them from interfering with each other during suppression. For example, in our case, max WH is 7680 and our class index is 2, so each box gets an offset of 2 times 7680, which is 15,360. This means that all bounding boxes belonging to class 2 are shifted by 15,360, ensuring they don't get mixed up with boxes from other classes during NMS. Next, we extract the confidence scores and store them in scores. These scores help rank the predictions so that during NMS, we keep only the most confident bounding boxes while suppressing redundant ones. Then, we adjust the bounding box coordinates by adding the class offset C, which again prevents overlapping detections from different classes from interfering with each other. Finally, we apply non-maximum suppression using torch vision. We pass in the adjusted bounding boxes, their confidence scores, and the IOU threshold, or intersection over union. IOU measures the overlap between two bounding boxes, and by setting a threshold, we can control how much overlap is allowed before suppressing a box. This function eliminates redundant detections, keeping only the most confident bounding box for each object. At the end of this step, I contains the indices of the final selected boxes after NMS, ensuring that we retain only the most relevant predictions. We can now run these final steps in our Colab notebook for those interested, adding completeness to our exploration. A couple of important aspects to note. First, as expected, NMS returned index 2 since it had the highest confidence score. All other predictions for the car, having lower confidence scores and overlapping beyond the IOU threshold, were suppressed. And finally, index 2 from I is used to index our X tensor, returning the winning prediction as the final output. To keep processing efficient, this line checks whether NMS has exceeded the allowed time limit. If it does, a warning is logged, just like in our case, and we break out of the loop early. However, the function still returns the output at the end, meaning we don't lose all results. Instead, some predictions may not have been fully processed by NMS before exiting, particularly in real-time scenarios. This ensures a balance between accuracy and speed. With our NMS results in hand, we return the output and move forward with our code exploration. Now that we have the predictions, we need to adjust them back to the original image dimensions. Since the model processes resized images, we use scale boxes to correctly map the detected bounding boxes to their original scale. So let's step into the scale boxes function. The first thing we do is calculate the gain or scale factor that was used to resize the input image before inference. In our case, this gain is 0.625, meaning the model received an image that was 62.5% of the original size. This factor tells us how much the height and width were scaled down. Next, we determine the padding factor, which accounts for any extra space added to maintain the YOLO stride dimensions. In this case, our resized image is 480 by 640, and since no padding was applied, the pad value is 00. That means the padding operations don't affect our bounding boxes here. However, what does matter is the division by the gain. This step rescales the predicted bounding box coordinates, which were based on the resized image, back to the original input size. Once we have the rescaled bounding boxes, we pass them through the clipboxes function. This function ensures that the bounding boxes stay within the image boundaries by clamping their coordinates. If any value is out of range, it is adjusted to fit within the valid dimensions. In our case, the bounding box is already contained within the image, so no changes occur, but it's a necessary step to prevent out-of-bounds detections. We can also run the same steps in Colab for better visualization. We download our tensors, so we are working with the exact same inputs, and load them. Here we can see the values that will be fed into the scale boxes function. Then we visualize the bounding box on the resized image. Since no padding was applied, padding is 0, the image remains unchanged. Finally, we apply the scale box transformation, and now we have the bounding boxes mapped correctly to the original image. When we overlay them, we can see that our predictions have been successfully restored to the original input size. Now that we have the adjusted bounding boxes, this line creates a results object for each image. Let's take a closer look at the results class. This class is designed to store and manipulate the outputs of the model. When we create an instance, we pass in the original image, its file path, class names, and the prediction results. The class also supports masks, probabilities, key points, and oriented bounding boxes, though these are not used in our case. By organizing these outputs into structured objects, the class makes it easy to access, process, and visualize detections. After initializing the results object, we append it to the list and return to predictor.py, wrapping up the post-processing steps and profiler. Now, for each image in the batch, we update the total count of processed images and record the time taken for pre-processing, inference, and post-processing. These values, measured in milliseconds and averaged across the batch, are stored in the speed dictionary inside each results object. This allows us to track performance metrics for each stage of the pipeline. Next, since the verbose and save arguments are set to true, we enter the relevant section of the code. As the name suggests, this function writes the inference results to a file or directory. We skip this part though, as our tensor has 4 dimensions, and these specific arguments are false in our case. This code extracts the frame number from a string by searching for a pattern like frame 23. If a match is found, it captures and converts the number into an integer. If no match is found, the frame is set to none, as in our case. Here, we define the path for saving label files, including the frame number if the input is a video. Next, we retrieve the corresponding result object and store the save directory for future use. We then move into the result.verbose function. This code extracts the detected boxes, and for each unique class, it counts the number of detections per class and adds this info to the log string, including the class name and an S if there's more than one detection. In our case, the log string ends up with the string 1 car. We then update the string, so it now contains the value 480 by 640, 1 car, along with the inference time in milliseconds. Finally, this code checks if the save or show arguments are enabled. If they are, it adds predictions to the image by calling the plot method of the result object. The plot method customizes the image display based on the provided arguments. Let's dive into that. We go all the way to the boxes and store them in pred boxes with show boxes set to true. This code initializes an annotator object, which is used to annotate images with prediction results. It takes a deep copy of the original image and sets the line width, font size, and font for the annotations. Finally, it passes the class names for annotation. Inside the annotator initialization, we calculate the line width, ensure the image data is contiguous, and set the font thickness and scale. We return the annotator object and continue with the code. Since predmasks is false, we skip that section. We are now at the plot detect results section. This code checks if predboxes is not none and if the show boxes flag is enabled. For each predicted box in predboxes, it extracts the class, confidence, and ID. It then constructs a label for the box, which includes the class name and confidence score if available. Next, the code uses the annotator.boxLabel method to draw the box and its label on the image. The box's color is determined based on the specified color mode, which can be set to class-based, instance-based, or other modes. If the box is an oriented bounding box, the rotation is also considered. Let's step into the box label function. We first determine the text color. We then go all the way to the bottom, where rotated is set to false. This code draws a rectangle on the image using OpenCV's rectangle function. It defines 2 points, P1 and P2, representing the top left and bottom right corners of the bounding box, respectively. The rectangle is drawn on the image with the specified color, line thickness, and anti-aliased line type. Since we have a label, specifically car 0.88, we step into this. The code adds the label to the image, positioning it near the bounding box. First, it calculates the width and height of the label text and adjusts for padding. It checks if the label fits outside the box and if it extends beyond the image's right edge, adjusting the position accordingly. Then, it draws a filled rectangle behind the label using cv2.rectangle and places the label text with cv2.putText, ensuring the label fits within the image boundaries and is properly positioned relative to the bounding box.